Hello everyone, I'm Chengzhou Tang from Simon Fraser University. In this video, I will introduce our work learning subspace minimization for low-level vision. The low-level vision tasks usually infer pixel-wise primitive information from images, so they can be handled by CNNs. Many CNN-based methods have been proposed in the past few years, and each of them has achieved state-of-the-art performance for an individual task. However, the fully CNN-based methods have their own limitations. Handling multiple tasks at the same time is difficult, especially for scenarios with limited computation budget or need real-time interaction. Training is also complicated and time-consuming, especially for applications beyond single image such as optic flow. Some other issues also exist, such as adversary attacks. So maybe we should find some inspirations from the method other than CNNs. Conventionally, we solve low-level tasks using energy minimization. The energy or object function contains the data term D, which is task-specific, and the smooth term R, which is general and task-agnostic. However, they also have some limitations. First, the data term is defined over pixel values or manual designed features, which is less expressive, and more importantly, the smoothest term assumes a specific distribution, which cannot describe the situation for each sample and each task. In this paper, we bridge the gap between the CNN-based method and the conventional energy minimization-based method, where we preserve the data term but upgrade the image pixel or manual features to the CNN features. More importantly, we assume that the desired solution is from lower dimensional subspace. Then we can use CNN to generate a set of basis vectors and represent the solution as a linear combination of these basis vectors, which is more adaptive than smoothness term. To this end, we build a simple feature pyramid to extract features. Then, at each iteration, we redefine the data term on the features and generate a set of basis vectors from CNNs, and finally minimizing the data term with subspace constraint. Besides the feature pyramid, only the basis generation is handled by CNNs, and it is general and task agnostic. So let's see how it works. We feed three kinds of information to the subspace generation networks. First is the derivatives of the data term at each pixel. Second is the downsampled image features from feature pyramid. And the third is a normalized rough solution, which can be 0 at the beginning of the process, or from the last iteration's output during the process. Then we use the integral image to aggregate the information in multi-scale and generate the final basis vectors through several residue blocks. With the generated basis vectors, we represent the incremental solution delta x as a linear combination of these basis vectors. And each iteration, we estimate the linear combination coefficient c. However, the subspace constraint will be violated during the iterative process. So we project a previous solution x to the current subspace, and then the subspace constraint is maintained. To demonstrate the proposed framework, we implemented two categories of applications. First are two binary segmentation tasks, including interactive segmentation and video object segmentation. Second are two dense correspondence tasks, including optic flow and stereo matching. For the experiment, we first test the joint multitask learning. In general, when the network structures are shared across tasks, we achieve slightly better or the same performance with other single-task CNN-based method. When both the networks and the structures and the parameters are shared, we achieve comparable results. We further do the zero-shot task generalization to prove the generality of the subspace generation, where we leave one task out for testing and train the network on the other tasks. Once the networks were trained, all the parameters are fixed, which is no worse than the conventional method for all tasks. And finally, we conduct ablation studies to test the necessity of the explicit minimization, the data term information for subspace generation, and the subspace projection operation. In summary, we propose to minimize the data term with subspace constraint generated from CNNs adaptively. It supports many low-level applications. We can share both the network structures and parameters for different tasks, and even support a plug-and-play a task which is unseen during training. Thank you. You are welcome to contact me for more details.